Tornadoes cause $1.1 billion in damage annually, despite advanced meteorology and reinforced construction. But in May 1883, an F3 tornado with 200 mph winds destroyed 9 homesteads across central Kansas, except one. William Morrison's house took 0 damage. Not a board shifted, not a window cracked. His family finished dinner while neighbors faced total devastation. Here's the impossible part. Morrison built this house in 1882 with basic hand tools and no engineering training. Neighbors called it a glorified storm cellar. The local carpenter declared, "No proper house belongs in a hole." Morrison spent $30 while neighbors invested over $200 in conventional cabins. When the ultimate test came, 9 engineered structures became scattered debris. Morrison's family never left the dinner table. What did this Kansas homesteader understand about tornado survival that our billion-dollar construction industry has completely forgotten? William Morrison arrived in central Kansas in 1880 with the same dream as thousands of other homesteaders. The Homestead Act promised 160 acres of prairie land to any man willing to work it for 5 years. Morrison claimed his quarter section in what would become the heart of Tornado Alley, 15 miles southeast of Great Bend. Like his neighbors, he built his first cabin using conventional wisdom. Timber frame construction, peaked roof, stone foundation. Quality materials hauled from the railroad depot at considerable expense. The structure cost him nearly $200 and 3 months of backbreaking labor, assisted by the traditional community barn raising. The tornado season of 1881 taught Morrison a harsh lesson about prairie reality. His well-built cabin, constructed according to established homesteading practice, became kindling in less than 2 minutes. The twister scattered his investment across 3 counties. Morrison's family survived only because they reached the storm cellar in time, huddled underground while their home disintegrated above. As he surveyed the wreckage, Morrison asked the question that would change everything. If the wind keeps destroying what's above ground, why build above ground at all? His neighbors rebuilt using the same methods, convinced that stronger construction and better materials were the answer. They invested in thicker timbers, more robust foundations, reinforced joints. The local carpenter, a skilled tradesman named Thomas Fletcher, advocated for conventional construction wisdom. Build sturdy structures above ground, he insisted, and add storm cellars for emergency shelter. Fletcher had built dozens of successful homestead cabins across central Kansas. His approach represented established expertise, proven methods, time-tested techniques. Morrison chose a radically different path. Instead of rebuilding above ground, he began digging. His neighbors watched with growing bewilderment as Morrison excavated what appeared to be an enormous rectangular hole, 20 feet by 24 feet, carved exactly 6 feet below the prairie surface. The project consumed 6 weeks of solitary labor. Morrison moved 2,880 cubic feet of Kansas clay with nothing but a spade, pick, and wheelbarrow. The neighbors' bewilderment turned to mockery. They accused him of laziness, taking the easy path by avoiding proper construction. Predictions of flooding filled coffee shop conversations. Concerns about living like gophers dominated Sunday dinner discussions. Fletcher made no attempt to hide his professional disdain. "No proper house belongs in a hole," he declared to anyone who would listen. The apparent absurdity seemed to confirm every suspicion. Morrison was installing full-sized windows facing south from an underground structure. He was carving proper rooms from prairie earth. He was building what looked like a conventional house layout, except the entire structure sat 6 feet below ground level. The project violated every principle of proper home construction that Fletcher had learned during 20 years of frontier building. But Morrison wasn't simply digging a hole. His systematic observations during the 1881 tornado had revealed something his neighbors missed. He had watched how prairie animals survived the storms. Ground-nesting birds emerged unharmed while tree dwellers perished. Buffalo wallows and prairie dog towns showed no wind damage year after year. Nature had perfected a survival strategy that human builders ignored. Morrison was translating millions of years of evolutionary wisdom into human habitation. The sophistication hidden in his apparent simplicity would soon face the ultimate test. Morrison's education began during the chaos of the 1881 tornado. While his neighbors focused on the destruction, Morrison observed the survivors. Ground-nesting plovers and meadowlarks emerged from the storm unharmed, their eggs intact in shallow prairie depressions. Meanwhile, tree-dwelling species suffered devastating losses. Robins, woodpeckers, and orioles that built in the cottonwoods along Walnut Creek were systematically eliminated. The pattern was unmistakable. Height meant death. Ground level meant survival. Morrison extended his observations beyond birds. Buffalo wallows dotted the landscape, circular depressions where massive herds had rolled and bathed for generations. These earthen bowls showed no wind damage year after year. Prairie dog towns sprawled across thousands of acres, intricate networks of underground tunnels and chambers. Tornadoes passed directly over these colonies without disturbing a single burrow entrance. The animals had solved the tornado problem through millions of years of natural selection. Every survivor used the same strategy: get below the wind's reach. The fatal flaw of above-ground construction became clear to Morrison through careful observation of tornado physics. Conventional cabins presented vertical surfaces for wind engagement. Tornadoes derived their destructive power from lifting and throwing structures, not simply pushing them over. The vertical walls that neighbors considered essential for proper construction were actually wine purchase points, giving the tornado something to grab and destroy. Morrison intuited what modern engineering would later confirm. Wind velocity decreases dramatically near ground level due to surface friction. At 6 feet below grade, wind speed approaches zero even in the most violent storms. Morrison's site selection demonstrated sophisticated understanding disguised as simple prairie common sense. He chose ground elevated just enough to avoid water collection, but not high enough to catch additional wind. The soil composition mattered crucially. Kansas clay provided the perfect balance, dense enough to resist collapse, porous enough to drain naturally. Morrison oriented his excavation to work with prevailing wind patterns, positioning the longest dimension perpendicular to the most common storm tracks. His drainage strategy sloped the excavation floor to channel water away from the structure, preventing the flooding that neighbors predicted would doom the project. Traditional wisdom merged with pioneer innovation in Morrison's approach. Earlier settlers had built sod houses, structures partially embedded in the earth for insulation and wind protection. But these were temporary shelters, crude accommodations until proper above-ground houses could be constructed. Morrison studied Native American earth lodge principles used by tribes across the Great Plains. The Pawnee and Omaha had perfected underground construction techniques centuries before European settlement. Morrison's crucial modification adapted these principles for permanent family residence rather than seasonal shelter. The technical specifications of Morrison's excavation revealed the precision hidden beneath apparent simplicity. 20 feet by 24 feet dug exactly 6 feet below grade. The dimensions weren't arbitrary. 24 feet provided sufficient interior space for a 4-room family home. 6 feet of earth cover guaranteed protection from the most severe tornado winds while maintaining reasonable excavation requirements. Morrison reinforced his earth walls with stone where available, but the wall system relied primarily on proper excavation angles to prevent collapse. Morrison's most critical decision involved the roof structure. Instead of building it below grade like a typical storm cellar, he positioned the roof at ground level. This choice transformed the project from a temporary shelter into a permanent residence. The roof would bear the entire structural load, transferring weight directly to undisturbed earth rather than excavated walls. Locally sourced timber, sod cutting, and basic tar paper would create a weather-resistant barrier that cost a fraction of conventional construction materials. Morrison was building a house that gave tornadoes nothing to destroy. Morrison's construction methodology revealed systematic thinking disguised as simple labor. Moving 2,180 cubic feet of Kansas clay required precise planning, not brute force. Morrison worked in 6-foot sections, excavating along the length of his planned structure to maintain wall stability throughout the process. His tool requirements demonstrated elegant efficiency: a basic spade for cutting earth, a pick for breaking through root systems, and a wheelbarrow for hauling dirt. Total equipment cost remained under $15 compared to the $200 his neighbors spent on lumber, nails, and hardware for conventional construction. Timeline comparisons told an even more remarkable story. Morrison completed his excavation in 6 weeks of solitary work, while above-ground construction required 3 months and community barn-raising assistance. The wall system Morrison developed solved multiple engineering challenges with a single approach. He cut his earth walls at precisely calculated angles to prevent collapse, creating natural buttresses that transferred load into undisturbed soil. Moisture management relied on understanding how water moved through prairie clay. Morrison carved shallow drainage channels within the wall structure itself, guiding groundwater away from living spaces without expensive gutters or foundation systems. His reinforcement strategy used locally available stones and timber sparingly, placing them only at critical stress points where earth alone might fail under seasonal freeze-thaw cycles. The insulation revelation came later. 6 feet of earth provided better temperature regulation than any building material available to Kansas homesteaders. Morrison's roof engineering represented his most critical insight. Unlike his neighbors who built walls to support roofs, Morrison designed his roof to carry the entire structural load independently. The earth walls served only as environmental barriers, not load-bearing elements. This fundamental difference allowed Morrison to use lighter, less expensive materials while achieving superior structural integrity. His locally sourced timber came from cottonwoods along Walnut Creek, milled with basic hand tools into adequate dimensional lumber. Sod cutting provided the primary roofing material, layers of prairie grass and roots that created a living membrane. Basic tar paper, the only purchased roofing component, cost less than $5 and provided essential moisture protection. Load distribution in Morrison's design transferred all structural stress directly to undisturbed earth rather than excavated walls. The roof beams extended past the excavation perimeter, resting on solid prairie ground that had supported buffalo herds for thousands of years. Weather resistance came from the sloping design that shed Kansas rainstorms away from the structure. The slight crown Morrison built into his roof prevented water collection while maintaining the low profile essential for wind deflection. The window innovation demonstrated Morrison's understanding of solar orientation and natural lighting. His south-facing windows maximized winter solar gain, reducing heating fuel requirements during harsh prairie winters. Glass acquisition required trading grain for window panes in Great Bend, the nearest railroad town 15 miles north. Morrison's ventilation system used temperature differentials between underground and surface air to create natural circulation. Cool earth-tempered air entered through lower vents while warmer interior air exited through higher openings. Light management through strategic window placement illuminated the entire underground interior without sacrificing structural integrity. Climate control mastery emerged from Morrison's earth-integrated design. Summer cooling relied on the Earth's constant temperature of 55 degrees Fahrenheit at 6-foot depth. Kansas summers regularly exceeded 100 degrees above ground, but Morrison's family enjoyed comfortable indoor temperatures without any cooling system. Winter heating required minimal wood burning due to natural earth insulation. Humidity control happened automatically as earth walls absorbed excess moisture during humid periods and released it during dry spells. Air quality remained excellent through natural circulation, preventing the stuffiness common in poorly ventilated dugout shelters. Morrison had engineered a climate-controlled environment using only natural systems. Morrison's success rested on 3 fundamental principles that conventional builders had never considered. The first principle eliminated wind purchase points entirely. Tornadoes derived their destructive power from lifting and throwing structures, not simply pushing them over. Conventional cabins presented vertical walls that gave wind something to grab and destroy. Morrison's solution presented no surfaces above ground level for tornado engagement. The aerodynamics were elegantly simple. Wind flowed over the rounded earth surface of his roof without finding grip points. Modern tornado-resistant construction now validates this principle, but Morrison discovered it through careful observation of prairie storms in 1882. The second principle achieved structural integrity through earth integration rather than fighting natural forces. Conventional wood frame construction relied on joints, fasteners, and material strength to resist wind pressure. Morrison's design eliminated the battle entirely by transferring all structural stress into the stable earth mass. Load distribution worked through compression rather than tension. Earth walls under compression can support enormous weight, while wood walls under tension fail when twisted by tornado winds. Morrison built his foundation in undisturbed prairie ground that had supported buffalo migrations for thousands of years. His structure became part of the earth itself rather than an object sitting precariously on top of it. The third principle integrated natural environmental systems instead of fighting them with artificial solutions. Temperature regulation used the Earth's thermal mass for year-round climate control. At 6 feet below grade, soil temperature remains constant regardless of surface weather extremes. Morrison's family enjoyed comfortable indoor temperatures, while neighbors endured scorching summers and brutal winters. Water management worked with natural drainage patterns rather than expensive gutters and foundation systems. Material acquisition utilized on-site resources, eliminating transportation costs and supply chain vulnerabilities. Maintenance requirements dropped to nearly zero since earth walls required no paint, shingles, or routine repairs that plagued wooden structures. The economics of Morrison's approach revealed the true cost of conventional construction wisdom. His total building investment of $30 compared to over $200 for standard homestead cabins. Labor efficiency showed even more dramatic advantages. Morrison completed construction in 40% less time, despite excavation requirements. Operational costs dropped by 80% due to minimal heating fuel needs. Longevity calculations favored earth-sheltered construction by decades. Neighbors faced recurring expenses for paint, roof repairs, and storm damage, while Morrison's maintenance costs remained virtually zero. The comfort revolution Morrison achieved challenged every assumption about underground living. Interior environment remained stable in temperature, humidity, and air quality throughout seasonal extremes. Space utilization provided full ceiling height throughout the structure, not the cramped conditions neighbors associated with dugout shelters. Family life proceeded normally with proper lighting, ventilation, and room layouts that accommodated standard domestic routines. Health benefits included reduced respiratory problems from stable humidity and temperature, plus natural quiet from earth insulation that blocked prairie wind noise. Integration with farming operations added practical advantages conventional builders never considered. Morrison's structure functioned as a root cellar for food storage while providing family shelter. Workshop space remained protected during severe weather, safeguarding valuable tools and equipment. Livestock instinctively sought shelter near the pit house during storms, recognizing the earth-level sanctuary that conventional structures couldn't provide. Morrison had created a homestead system that worked with prairie realities instead of fighting them with expensive materials and feudal engineering. The meteorological conditions of May 15, 1883, created perfect tornado formation weather across central Kansas. A powerful low-pressure system collided with dry air masses, generating the atmospheric instability that spawns violent storms. Morrison's neighbors recognized the danger signs: the peculiar green tint to afternoon skies, the sudden temperature drop, the eerie calm that preceded prairie storms. Conventional wisdom dictated immediate retreat to storm cellars and basements, underground refuges designed for emergency shelter during tornado passages. The Morrison family responded differently. They remained in their normal living space, continuing dinner preparations while neighbors abandoned their homes for cramped emergency shelters. The approaching tornado measured F3 intensity on modern scales, generating sustained winds exceeding 200 miles per hour. The funnel cloud carved a precise 2-mile path of destruction across the prairie, systematically testing every structure in its way. Morrison's earth-integrated home lay directly in the tornado's path, between the Henderson farm and the Schmidt homestead. Both conventional structures would provide definitive comparison data for Morrison's radical construction method. The test results validated Morrison's principles with devastating clarity. 9 conventional homestead structures suffered complete destruction within the tornado's 2-mile corridor. The Henderson cabin became scattered lumber distributed across 3 counties. The Schmidt home disappeared entirely, leaving only foundation stones to mark its former location. Barns, outbuildings, and storm cellars sustained varying degrees of damage from direct tornado impact and flying debris. Morrison's outcome stood in stark contrast: 0 structural damage. His family continued their evening meal while the tornado passed overhead. The roof showed no displacement, no shingle loss, no structural stress indicators. Windows remained intact. Interior furnishings stayed undisturbed. The aerodynamic proof appeared in the debris field analysis. Wreckage from destroyed structures created distinct scatter patterns, showing materials blown over Morrison's property rather than into it. The tornado had nothing to engage, no vertical surfaces to grip and destroy. Morrison's house remained invisible to the wind, integrated so completely with the earth that the storm passed without recognition. Community response shifted dramatically within hours of the tornado's passage. Mockery transformed into desperate interest as neighbors calculated reconstruction costs while Morrison faced 0 expenses. The local newspaper documented the contrast between widespread destruction and Morrison's miraculous survival. Thomas Fletcher, the carpenter who had proclaimed that no proper house belonged in a hole, arrived at Morrison's door requesting detailed construction information for his own family's safety. Knowledge transfer accelerated rapidly throughout the region. Within 2 years of the 1883 tornado, 7 families had constructed earth-sheltered homes using Morrison's principles. Each family adapted the basic approach to their specific sites and requirements, but all incorporated the fundamental insights: elimination of wind purchase points, structural integration with earth masses, and natural environmental systems utilization. Performance validation continued through subsequent severe weather events. Every earth-sheltered home in the area survived later tornado encounters without damage. Morrison's true innovation extended beyond construction technique to philosophical approach. He had recognized that the best tornado shelter was a house that gave tornadoes nothing to destroy. His method represented humility before natural forces, working with environmental systems rather than attempting to dominate them through expensive materials and complex engineering. The enduring lesson challenged conventional assumptions about protection and shelter. Sometimes the most radical solution hiding in plain sight was also the most obvious one. Morrison proved that survival wisdom often contradicts human intuition, but nature provides the answers for those willing to observe and learn.